Look around you. What do you see? A chair, a table, the air you breathe. Look up at the night sky. You see stars, planets, entire galaxies. From the smallest grain of sand to the most distant star, all made of the same stuff. It's true. This is called matter. Matter is made of tiny particles, atoms. We call them atoms. They are the building blocks of the universe. For a long time we thought atoms were indivisible. The word comes from Greek atomos, uncuttable. Imagine a piece of gold, cut it in half, cut again, cut again. Eventually you'd reach a single atom of gold. That atom still behaves like gold. Everything around you is a massive collection of atoms bonded together. Atoms are unimaginably tiny. More atoms in a glass of water than glasses of water in all the oceans. Our existence is a performance by these particles, dancing to cosmic laws. So, the next time you take a breath, remember what you're doing. You are inhaling trillions upon trillions of atoms. For a long time we pictured the atom as a simple, solid ball, a tiny, indivisible sphere. But science is a journey of discovery, and our picture of the atom was about to get a lot more interesting. Ernest Rutherford decided to probe the atom. He fired tiny particles at a thin sheet of gold foil. He expected them to pass straight through. Most did. Some, very few, bounced back. It was shocking. Rutherford said it was like firing a 15-inch shell at tissue paper and having it hit you. The atom wasn't a solid ball. It was mostly empty space. Nearly all mass was in a tiny, dense, positively charged center. He called it the nucleus. It was what the particles were bouncing off. The nucleus is the heart of the atom, the sun of a tiny solar system. If an atom were a sports stadium, the nucleus would be a marble at the center. It contains more than 99.9% of the atom's mass. A teaspoon of nuclear material would weigh billions of tons. The nucleus determines an element. Hydrogen, helium, gold, uranium. It's the command center. The atom's identity. To understand the universe, we must understand the nucleus. We must venture into the heart of the atom. So we've journeyed into the atom and found its dense central nucleus. But what is this nucleus made of? And what about the rest of the atom, that vast expanse of empty space? It turns out the atom is a family of three main particles: protons, neutrons, electrons. Two of them live together in the nucleus. One orbits from a distance. Let's start with the inhabitants of the nucleus. First, the proton. It carries a positive electrical charge. Think of it as the particle of identity. The number of protons defines an element. 1 proton, hydrogen. 2 protons, helium. 79 protons, gold. Next, the neutron. Electrically neutral, no charge. About the same size and mass as a proton. It acts as a peacemaker in the nucleus. Protons repel each other because like charges push apart. Finally, the electron. Tiny, much smaller and lighter than protons or neutrons. It carries a negative charge, opposite the proton. Electrons live outside the nucleus. They move in complex orbits or shells around it. In neutral atoms, electrons equal protons. Their negative charges balance the nucleus's positive charge. Electrons are the atom's face to the world, governing how it interacts and bonds with other atoms. We have a puzzle. A big one. The nucleus is packed with positively charged protons. Like charges repel. Basic physics. They should be pushing each other apart with tremendous force. The electrical repulsion inside a nucleus is enormous. So why doesn't the nucleus just fly apart? Why do atoms even exist? There must be another force at play. A force far stronger than the electrical force. But it only works over incredibly short distances. It can act like cosmic superglue, holding protons and neutrons together. This is the strong nuclear force. It's the strongest of the 4 fundamental forces. About 137 times stronger than the electromagnetic force. It binds protons and neutrons, collectively called nucleons. It doesn't care about electric charge. It pulls protons to protons. It pulls neutrons to neutrons. It pulls protons to neutrons, all with equal strength. It overcomes mutual repulsion and locks the nucleus into a stable state. But the strong force has a very short range. It operates only across distances about the size of a nucleus. Pull 2 protons apart slightly, and the strong force drops to 0 almost instantly. That's why we don't feel it in everyday life. A powerful giant confined to the atomic nucleus. Imagine holding a group of powerful, angry dogs on very short leashes. The dogs, the protons, are trying to run away. Your grip on the leashes is the strong nuclear force. As long as the dogs stay close, you can hold them. But if one gets just a little too far, the leash snaps. Very large nuclei with many protons can become unstable. The nucleus gets so big that protons on opposite sides are too far for the strong force to hold. That instability drives radioactivity and nuclear power. We've met the powerful giant, the strong nuclear force which holds the nucleus together. Now let's meet its more subtle sibling, the weak nuclear force. As its name implies, it is much weaker than the strong force. It is also weaker than the electromagnetic force. But don't let its name fool you. The weak force is responsible for one of the most fundamental processes in the universe, the ability of a particle to change its identity. It is the force of transformation. It allows a neutron to turn into a proton. It can also allow a proton to become a neutron. This process is at the heart of a type of radioactivity called beta decay. Imagine a nucleus with a few too many neutrons. It's unbalanced. The weak nuclear force can step in and fix it. It causes one of those extra neutrons to transform. The neutron, neutral in charge, becomes a proton, which is positive. To conserve charge, the process emits an electron, negative, and a tiny, almost massless antineutrino. The atom ends up with one more proton and becomes a different element. For example, carbon-14 decays into nitrogen-14. Beta decay is incredibly important. It's one of the reasons the sun shines. Deep in the sun's core, immense pressure lets the weak force turn protons into neutrons. That's a key step in nuclear fusion that powers the sun, converting hydrogen into helium, and releasing enormous energy that warms Earth and enables life. Without the weak force, stars couldn't burn their fuel properly. The universe would be darker, colder, and far less interesting. It controls the rate of certain radioactive decays, which lets us use carbon dating to date ancient artifacts and fossils. The weak force gives us a cosmic clock, letting us read history in the bones of the Earth and the light of the stars. The forces holding the nucleus together are, honestly, just immense. The strong nuclear force binds protons and neutrons with an incredible amount of energy. This is called binding energy. Now, what if we could tap into that energy? What if we could rearrange the nucleons inside a nucleus and release some of that power? Well, this is the central idea behind nuclear energy. There are two main ways to do this: fission and fusion. Fission means to split, breaking a large, heavy, unstable nucleus into two smaller, more stable nuclei. The most famous element used for fission is a specific type of uranium, uranium-235. Its nucleus is large and just barely stable. Hit a U-235 nucleus with a slow neutron, it absorbs the neutron, becomes highly unstable, and splits apart. It breaks into two smaller atoms, releases a few extra neutrons, and a tremendous amount of energy. That energy, from the change in binding energy, is millions of times greater than a chemical reaction like burning coal or gasoline. Now here's where it gets interesting. Those extra neutrons can strike other U-235 atoms, causing them to split too. Each split releases more neutrons, which cause more splits, and so on. A chain reaction. In a reactor, the chain reaction is carefully controlled. Control rods absorb some neutrons, keeping the rate steady and manageable. The heat boils water, creates steam, turns turbines, and generates electricity for our cities, without greenhouse gases. The other method is fusion, which means join together. Take two small light nuclei like hydrogen isotopes, force them together to form helium. This powers the sun and all the stars. When light nuclei fuse, they release enormous energy. Fusion could be cleaner and more powerful than fission, using abundant hydrogen from water. But creating star-like temperatures and pressures on Earth is one of the greatest scientific challenges of our time. Scientists are working on tokamak reactors and other fusion technologies to harness this stellar power for clean energy. The power of the nucleus isn't just for creating energy or understanding the stars, it has a much more personal and profound application: saving lives. The field of nuclear medicine uses the properties of radioactive atoms called radioisotopes to diagnose and treat diseases. Doctors can introduce a small, safe amount of a radioisotope into a patient's body. This substance, called a radiotracer, accumulates in a specific organ or tissue. As the radioisotope decays, it emits radiation like gamma rays. These rays are detected by a PET scanner outside the body. The scanner creates a detailed image showing structure and how it is functioning. It can reveal blood flow, metabolic activity, the presence of tumors long before a standard X-ray. This ability to see function is a game changer. For example, a PET scan can show if cancer has spread to other parts of the body, helping doctors choose the most effective treatment. It can show areas of the brain active during a task, helping us understand how our minds work. It can reveal blockages in the heart's arteries, helping to prevent heart attacks. These techniques provide a window into the living, working body unimaginable a century ago. They allow earlier and more accurate diagnoses, leading to better outcomes for millions each year. Beyond diagnosis, nuclear physics provides powerful tools for treatment. Radiation therapy aims high-energy radiation precisely at tumors. That radiation damages cancer DNA, destroying cells or stopping division, while minimizing harm to healthy tissue. Nuclear medicine shows we can wield the atom's power with precision and compassion. Our journey into the atom's core has revealed a force of, honestly, unimaginable power. This power, like so many great discoveries in science, presents humanity with a choice. The discovery of nuclear power came with a steep learning curve, and with it, the risk of accidents. 3 Mile Island, Chernobyl, Fukushima. These accidents highlight the absolute necessity for robust safety protocols. The legacy of these events has, understandably, created a great deal of public fear and skepticism about nuclear power. Understanding nuclear physics isn't just about appreciating the science, it's about being an informed citizen. It's about being able to weigh the risks and benefits of this powerful technology, and participate in the crucial conversation about our nuclear future. So, we've traveled from the vastness of the cosmos to the infinitesimal realm of the atomic nucleus. We've seen how a few simple particles, protons, neutrons, electrons, governed by a handful of fundamental forces, build everything in the universe. We've seen how the nucleus, that tiny, dense heart of the atom, holds the key to incredible power. A power that can light up our cities, heal our bodies, and help us read the history of the universe. A power that also carries with it immense responsibility and risk. So, why does all this matter to you? It matters because nuclear physics is not some abstract, far-off field of study. It is woven into the fabric of our modern world. The device you are using to read this, the electricity that powers it, the medical technologies that keep us healthy, and the geopolitical landscape of our planet are all shaped by our understanding of the atom. In an age where we face the monumental challenge of climate change, nuclear fission offers a proven source of vast, carbon-free energy. And on the horizon, the dream of nuclear fusion, mimicking the sun on Earth, promises a future of nearly limitless clean power. Understanding the basics of nuclear physics empowers you. It allows you to look past the headlines and the science fiction and engage with the real issues. It helps you understand the debates about energy policy, medical ethics, and international security. It gives you the tools to ask critical questions about safety, waste disposal, and the difference between a controlled reaction in a power plant and an uncontrolled one in a bomb. An informed public is the most important ingredient for making wise decisions about how we use this profound knowledge. Knowledge is power, and knowledge of nuclear power is essential for a safe and prosperous future. The study of the atom is a fundamentally human endeavor. It stems from our innate curiosity, our deep-seated desire to understand our world and our place in the cosmos. What are we made of? Where did it all come from? The quest to answer these questions has led us to the heart of stars and to the core of matter itself. Nuclear physics is a testament to what we can achieve when we are driven by curiosity and a passion for discovery. It is a story of incredible intellectual achievement, and it is a story that is far from over. The next chapter is ours to write, and it begins with understanding the mind-blowing science locked within the heart of the atom.